Good morning. We are looking at section 4.4, indeterminate forms and L'Hopital's rule. We looked at the Rolle's theorem and the mean value theorem. And in both cases, we're going to start with continuity and differentiability, and we have to prove that to move on. In the case of Rolle's theorem, we also show the third criterion, f of a equals f of b, and then we find f prime of c that must be 0. The mean value theorem doesn't have that criteria. Summary of how derivatives affect the shape of a graph. Okay. And now indeterminate forms and L'Hopital's rule. Here's the synopsis of what is going on. And in short, when you want to take the limit, okay, if the result is 0 over 0 or infinity over infinity, as we come across this stuff often, okay, then we can replace the f and g with, let me just fix this class. This is g and so is this one. We can take the derivative of that and do the math. That's the idea behind the L'Hopital's rule. Okay, so having said that, the idea is that there's a struggle, okay, when you look at the top and the bottom as x approaches a specific number, okay? And in some cases, we can use different techniques we have used. For example, factoring did the job here, okay? In this case, we used geometry in conjunction with trigonometry to show that, okay? And the idea is that there is a struggle between the top and the bottom. And so what happens, which one approaches 0, which one approaches infinity, or some other number they will get into. And so that's the idea behind this method. And now practically just about everything can be done with the L'Hopital's rule, as long as it ends up being 0, 0, 0 over 0, or infinity over infinity. So your first step is to show it's either one, and then we move on. So for example, if we are looking at this one, first you have to show that the top and the bottom are both 0. So your first step of the business is to say this is equal to 0 over 0. And again, obviously you see why. ln of 1 is 0, 1 minus 1 is 0. So first you indicate it's 0 over 0 when you plug in, okay? Therefore, you can use the L'Hopital's rule. What does L'Hopital's rule tell us? Just differentiate the top, okay, and the bottom separately. This is not a quotient rule class. The top gives you 1 over x. The bottom gives you simply 1. So take a look. So the limit as x approaches 1, the top differentiation gives you 1 over x, and the bottom gives you 1. Now simplify this complex fraction. Obviously, this is a complex fraction, which gives you 1 over x. And now plug in, obviously, the answer is 1 over 1 or 1. I hope everybody understands what's happening. You have to plug in, come up with either 0 over 0 or infinity over infinity to justify using L'Hopital's rule, or you cannot do that. So I hope everybody's clear on that. So let's look at the next one and see what happens. Plug in. If we plug in 0 here, okay, we get e to the power of 0, which is 1, minus e to the power of 0, which is 1. They cancel each other. And then minus 2 times 0 is 0. So the top is 0. The bottom is 0, minus sine of 0, which is also 0. So quickly, we show that it's 0 over 0. Don't assume it is, because it may not be. Okay, even if you do it in your head properly, that's absolutely fine. So L'Hopital's rule says let's differentiate the top. So e to the power of x gives us e to the power of x minus e to the power of minus x gives it e to the power minus x times negative 1, so makes it positive. Minus 2x becomes minus 2. So the numerator is done. The bottom x 1 minus sine gives us cosine. So we are doing it piece by piece. Again, I want to make sure everybody understands that the derivative of negative e to the power of negative x becomes positive, okay? All right, plug in. You get 1 plus 1 minus 2, 0. Cosine of 0 is 1. And I hope you see that you get 0 over 0. Again, so you can use L'Hopital's rule again. Let's differentiate. The top gives you itself, e to the power of x. The bottom, the second one, e to the power of minus x is itself times negative 1. So minus e to the power of minus x, and this is a constant. Okay. 1 gives you 0. Minus cosine gives you negative sign, so that results in positive sign. Plug in. Well, the top is 1 minus 1 or 0. The bottom is 0. Again, let's do L'Hopital's rule. I picked this question on purpose because it really illustrates the power of L'Hopital's rule. You do it many times as you want. Differentiate. Well, e to the power of x is itself, and this one becomes plus e to the power minus x. We've done it many times. Sine gives you cosine. Again, I want to emphasize this is not a quotient rule because I've seen students mixing them up. Now, if you plug in 0, you get 1 plus 1 over cosine of 0, which is also 1. And you are done. I think this example is a fantastic example because it really gives you the essence of L'Hopital's rule. And if you understood this one, okay, you are in good shape, class. You are in good shape. All right. I'm sure you remember, okay, first and foremost, if you plug in, you get 0 over 0. And we had discussed when we get 0 over 0 or infinity over infinity, it simply means indeterminate and therefore more work. Everybody remembers that. Now, what I'm trying to say is that, can you do by factoring as before? Of course. Okay. Now that we have the L'Hopital's rule, let's try the L'Hopital's rule also. Okay. So if we did it by factoring, it'll look something like this. Okay. X minus 2 drops. And you plug in and you get 5. Okay. If we did it by L'Hopital's rule, everybody, this would be the limit as x approaches 2, x squared, 2x, x, 1, the denominator is 1. And if you plug in number 2, you get to the same answer. So the old rule, the new rule, it doesn't matter. L'Hopital's rule, you can use L'Hopital's rule from now on. Okay. All right. Let's look at the next one. If we plug in infinity, everybody, we get ln of infinity, ln of square root of infinity, which is infinity, over infinity squared, which is infinity. So the result is infinity over infinity. Okay. So we can do by L'Hopital's rule. All right. How do you differentiate the natural log? Flip it over. 1 over square root of x, and then times the derivative of square root of x. By now, you know it's 1 over 2 square root of x. I hope you do because we've done it many times. X squared gives you 2x. So I'm assuming everybody knows the process. 1 over square root of x, okay, 1 over 2 square root of x. Or simply put, change this, okay? Or just change this to 1/2 ln x, okay? And differentiate it that way. Okay, class? That actually may be faster. Either way, here's what you get, because the product of these two is 2x. It's a complex fraction, and it becomes 1/4x squared. Replace the x with infinity, and you get 0. So there are two ways to differentiate that natural log piece. Okay, class? There are two ways to do that. Probably changing the square root of x is better, but I thought it was simple enough either way. It's not that big of a deal. So at least you've seen them both now. Okay, theta is approaching pi/2. So when we plug in, we get 1 minus sine of pi/2, 1 minus sine of pi/2 over cosecant pi/2. Okay. And by the way, cosecant is 1/sine. So it happened to become 0/1, and you're done. I want to make sure everybody understands again what happens. Let's just actually write this for one moment. So this, when you plug in, becomes 1 minus sine pi/2 cosecant pi/2. Now sine of pi/2 is 1, so is cosecant pi/2, because cosecant is 1/sine. In other words, you plug in and it works out and you're done. You don't have to do anything else. In this case, if you plug in 0, both of them are cosine at top, becomes 0/0. Cosine of 0 is 1, remember that, okay? 1 minus 1. And so you do L'Hopital's rule. So let's differentiate the top. Cosine becomes negative sine and times m. So negative m sine mx minus cosine becomes negative sine nx, and then times n, the denominator is 2x. So one more time, cosine gives you negative sine, and then times m, minus cosine gives you negative sine, that's why we get plus, and then times n. Okay, everybody? Times n. I divide by 2x, everybody's happy. And now we plug in, and I hope you see that in both cases it's sine and becomes 0. The denominator is also 0, which means 0/0, which means L'Hopital's rule. Again, okay. All right, so minus m remains. Sine gives you cosine and then times m. So minus m times m minus m squared cosine mx. This is done. Now this one, n times, okay, sine gives you cosine and then times n, so plus n squared. The bottom is simply 2. Okay. So let's recap. I want to make sure we understand what happened. Negative m is there. It's a multiplier. Remember, m and n are constant. Sine mx, it's cosine mx times m, resulting in minus m squared cosine mx. N remains as a coefficient. Sine nx gives you cosine nx times n, and that's why we get n squared. Now, if we replace the x with 0, the denominator is 2. The top, this one goes to 1, so minus m squared. This one goes to 1 because it's a cosine also, and n squared. And this is your final answer. I hope everybody's clear on that, class. So when we have 0 over 0, infinity over infinity, we can use L'Hopital's rule. Okay. What if we have 0 times infinity? If it's in the shape of 0 times infinity, we can make it as f over 1 over g, or g over 1 over f, and it either becomes 0 over 0 or infinity over infinity. Now, just as an example, the limit of x ln x as x approaches 0 from the right, okay? I hope you see 0 from the right makes x 0, makes ln x negative infinity, okay? Now, by the way, 0 times infinity or 0 times negative infinity is the form anyways that we are discussing. Now, here's the question. Which one goes down? Can I write the limit as x approaches 0 from the right of x over 1 over ln x, or ln x over 1 over x? You can write both of them. Okay, you can write both of them. Generally speaking, if you're careful, both of them will answer, but most of the time, one is a lot easier than the other. And so it may take a long time to do one versus another. That's all I'm saying. So, so how do you know which one you take down? Ultimately, it's a trial and error. However, the one that you take down, it shouldn't be easy, too difficult to differentiate. So when I take the x down, becomes 1 over x. Okay, class. And by the way, notice the moment it goes down, understand the numerator is negative infinity. The numerator is negative infinity, okay? But the denominator is infinity. In other words, so it's negative, class, okay? Because ln of, if you want to be more specific, it's minus infinity. So what I want to make a point of is that, again, we can use L'Hopital's rule, and that means we can use differentiation of the top over the differentiation of the bottom. And that's my point. The top is easy to differentiate, is 1 over x, and the bottom is not too bad either. 1 over x, by now you know it's negative 1 over x squared. If you don't, just write it as x to the power of negative 1 and differentiate. By now, I think we should have an easy time understanding what happens. So this is a complex fraction, okay? I hope you see that it becomes negative x, right? This whole fraction becomes negative x. And now when you plug in, you get 0. And you're done, okay? All right, let's plug in infinity, okay? When you plug in infinity, this piece goes to infinity. This piece goes to 0. The reason it goes to 0, it's minus x over 2, or minus infinity. E to the power minus infinity is 0 because it's 1 over e to the power of infinity. So I hope you see that this gives you infinity, this gives you 0. So take one of them down. I hope you see I can take square root of x down and write it 1 over square root of x, or I can take this piece down. If I take square root of x down, it's more difficult. But this actually fairly easy. Negative goes down and it becomes positive. And now both of them are infinity, the top as well as the bottom. And so I can use the L'Hopital's rule. Okay, L'Hopital's rule. And so I differentiate the top, 1 over 2 square root of x. I differentiate the bottom, the same thing, e to the power of x over 2 times 1/2, or divided by 2. Those are easy differentiation. I'm going to assume we are comfortable with differentiation. So recap, square root of x, 1 over 2 square root of x. And again, if need be, change it to x to the power 1/2 to the math. Exponential is always itself and times the derivative of the exponent, which is 1/2. Don't forget to keep up with the limit. Okay, keep up with the limit. All right. Now, I hope you see the 2 at the very bottom and the 2 here, they cancel out. So the 2's cancel out. Okay. And here's what we end up with when we simplify this complex fraction, everybody. Now what happens? This is infinity. This is infinity. 1 over infinity times infinity is 0. By the way, I hope nobody has any problem with a complex fraction, okay? It still cancels out these two. Okay. Okay. So the form 0 times infinity or negative infinity, we can make it such that it becomes 0 over 0 or infinity over infinity. By the way, if you move them the other way around, would in both cases become 0 over 0, okay? Whatever is easier to differentiate. All right. We have cases that are in the form of infinity minus infinity. They are also considered to be indeterminate form. Okay, so we are looking at various forms of indeterminate. And to take care of the business, again, ultimately, we can only use the L'Hopital's rule if we go with what? 0 over 0 or infinity over infinity. And so many times taking a common denominator will do the job. So let's look at this one, for example. Okay. Cosecant x, remember cosecant is 1 over sine. Okay. And cotangent is 1 over tangent as an example, or all you have to do for this case, remember x is approaching 0, and I hope you remember the graph. So in both cases, we end up with infinity. Okay, so this is 1 over 0 from the right, so it's infinity. And cotangent on the right of 0 is also infinity, assuming we are okay with all of this. So having said that, the process is to take the common denominator. How? This is 1 over sine. Cosecant is 1 over sine. Cotangent is cosine over sine. Again, don't forget, I did say it's 1 over tangent. That was explanation as to one way to get to infinity. But if I am taking a common denominator, I should look at a different format for that. Now, take a common denominator of sine. And I hope you see that if you plug in, replace the x with 0, cosine 0 is 1, so we get 1 minus 1, which is 0, sine 0 is 0. So now we can use L'Hopital's rule because we have 0 over 0. Let's differentiate the top. This is minus, so minus. The derivative of cosine is negative sine, so it gives us positive sine x. Okay, and the denominator is cosine. Now, replace it with 0. Sine of 0 gives you 0. Cosine of 0 gives you 1. The answer is 0 over 1, 0 over 1, or simply 0. All right. As we approach 1 from the right, okay, each one of these cases becomes 0, class. Okay, let me just write this. When you plug in, if you plug in 1 from the right, this goes to 0. This goes to 0 from the right. And each case is negative infinity. Okay. ln of 0 from the right is negative infinity. And all you have to do is just remember the graph. So you're looking at infinity minus infinity or minus infinity plus infinity, however you want to look at. So how do we deal with that? Let's put the logs together. Okay. It's been decomposed. So when we put them together, we get ln of x to the power of 7 minus 1 over x to the power of 5 minus 1. Okay. And basically, you can take a limit of this. You can interchange those two if you want because it's a limit and natural log. So when it's continuous, you can do that. So the bottom line is let's take a limit of this piece. And when we do that, okay, it becomes ln of, now plug in and you get 0 over 0. For this part, which is 0 over 0, we can use L'Hopital's rule. So this gives you 7x to the power of 6, and this one gives you 5x to the power of 4. We are differentiating the top, we are differentiating the bottom. ln remains outside. The limit as x approaches 1 from the right remains. You just differentiate the top, you just differentiate the bottom. Plug in, it happened to work out because this gives you 7, this gives you 5, so it's ln of 7/5, and you can leave it like that, or you can say it's ln of 7 minus ln of 5. It doesn't matter, it's an exact answer. You don't want to write the approximation for that. All right. We are looking at the same situation. If you let one x approaches 1, this is 1 from the right, okay? So you're dividing by 0, you're dividing by 0, okay? And you are dealing with infinity, okay? And so you are going to use a method which is LCD, okay? LCD. And taking a common denominator means ln x times x minus 1 is a common denominator. 1 times x minus 1 minus 1 times ln x over the common denominator. So again, when you plug in, you get infinity minus infinity, and now you are going to take a common denominator. That I hope is not a problem. Okay. So what comes next? Let's plug in. When we plug in 1, we get 1 minus 1, which is 0, minus ln 1, which is 0. So the top goes away and becomes 0. 1 minus 1, okay, is 0, times ln 1, which is 0. So 0 over 0. Okay, 0 over 0. L'Hopital's rule is in order. We are going to use the L'Hopital's rule by differentiation. The top gives us 1 minus 0 minus 1 over x. The bottom, x minus 1. We can multiply and do the math, or we just do it just the way it is. X minus 1, okay, times ln x, okay. One way is to use the product rule on that. So x minus 1 gives you 1 times ln x gives you 1 over x times x minus 1, in any order that you put it, okay. Or you can say, just as I mentioned, you know, x minus 1, 1 times s, so it's a different, slightly different order, it doesn't matter, okay. Now, this is a complex fraction. If we multiply the top and the bottom by x, we see that we can get rid of this. The reason I say it's a complex fraction, you have a fraction here, you have a fraction here. So this gives you x minus 1, okay. Then this one goes away, becomes x minus 1, and this becomes ln x times x, or x ln x. I hope you're comfortable with complex fractions. So one more time, if you, let me just move this. Let's put this closer to this fraction bar. So x over x, okay, class. All right, and so if we plug in again, we get 0 over 0. I hope you see that, okay. Plug in 1, you get 0, and the same thing for the bottom, 0 over 0. L'Hopital's rule, okay. By the way, x ln x class, x ln x, we proved it. If you go back to previous example, we proved this was 0, okay. It's important to know that. But in any event, so you really have to look at the fact that you're taking a limit. And having said that, because remember what it becomes when you plug in 1, you get 1 here and ln of 1 from the right. So with that being the case, let's just differentiate it again. Okay. X minus 1 gives you 1. X gives you 1. Okay. Now minus 1 gives you 0, and this is a product rule, class X, 1 times ln x. ln x, 1 over x times x. Okay. And this gives you 1. 1 and 1, they add up to 2. So I hope you see this is 1. So you get 1 over 2 plus ln x. X is approaching 1 from the right. If I replace the x with 1, ln 1 becomes 0. The answer is 1/2. The answer is 1/2. Okay. The answer is 1/2.
Professor?
Yes.
Could you please go back to the previous slide for 1 second?
I'm sorry, a little bit louder, please.
Can you please go back to the previous slide for 1 second?
Which one? This one?
The previous one, before that one.
This one?
No, like the slide.
Over here?
Like the previous slide, like the slide that we did for example 4.
Okay, you're talking about this one?
Yes.
Actually, this x is not approaching 0. I thought it was approaching 0. We don't need that class. My apologies.
Okay.
We don't need that. Because for a moment, I thought it was 0. This is approaching 1. We don't need that. Okay. Because simply x is 1, ln 1 is 0. So this thing is 0. When you plug in, okay, 1 times ln 1. And ln 1 is 0, their product is 0. So you don't need that. Okay. Now, we also have cases such as 0 to the power of 0, infinity to the power of 0, 1 to the power of infinity, that are considered indeterminate as well, okay? And the technique is to use natural log. That's one way to do that. When we come across the function and we set it equal to y, remember, this is what you are working with. If you call this y and take the natural log, g of x becomes a coefficient. And you work on this, and you finish the job, again, by the method of the L'Hopital's rule. Whenever you're done, your final answer will be as follows, class. Your final answer, whatever this gives you, then the answer will be e to this power. Let's say it's, I'm going to put an asterisk. Okay, if you work this out and it gives you any answer, e to that power is the answer. So this is one way we can handle this. It is also possible to write it as an exponential, okay, with the base b. You can do that. I'll show you in one example quickly. So here's an example. The limit of e to the power of x plus x to the power of 1 over x as x approaches infinity. I hope you see that this is infinity because it's e to the power of infinity. This is infinity. The whole thing becomes infinity, and 1 over infinity is 0. So you're looking at infinity to the power of 0. The bottom line is, I'm going to remind you, when we differentiated a function that was in the form of f of x to the power of g of x, we did logarithmic differentiation. We set it equal to y, and then we took the natural log of both sides and implicit differentiation. The process is similar to that. So we are going to give it a name y, this function, because it makes life easier. And then we take the natural log of both sides, and the result is that ln y becomes now 1 over x. This 1 over x sits in front according to logarithmic properties. And now we are going to work on this. And as I mentioned, whatever the answer, whenever you're done, let's say the answer is 10, then your answer for the original question would be e to the power of 10, anything that you get, okay? So we are taking the derivative of this piece, okay? We are taking the limit of this piece, okay? And as you can see, we can put this one at top, this one at the bottom, and it becomes infinity over infinity. So the x is the denominator. We just expand this fraction bar. Again, we are not doing anything else. We are expanding the fraction bar. Okay, so the top, it's infinity. Ln of infinity is infinity. The bottom is infinity. Infinity over infinity means we can use L'Hopital's rule. Okay, how do we do that? Let's differentiate the top. So we flip over the natural log, the argument of natural log. So 1 over e to the power of x plus x. And then we multiply by its derivative, which is e to the power of x plus 1. Over the derivative of x is simply 1. So this fraction, okay, so again, flipped over. And then this fraction, we rewrite this. This is really not a complex fraction, as follows. Okay, so this is the denominator. We extend this fraction bar, and this is 1. It has no effect. So this is again infinity over infinity. Let's continue with the thought. So we are going to differentiate the top, becomes e to the power of x, and the bottom becomes e to the power of x plus 1. And I hope you see that's infinity over infinity. Differentiate the top is itself, and the bottom is e to the power of x, and we are practically done because this is equal to 1. And remember what I told you. Whatever is the answer, then the answer for the original question will be e to this power, so e to the power of 1. And the reason why is very simple. We didn't get the y, we got the limit of ln y as x approaches infinity is 1. That's what we found. So I show you the process. You don't even have to worry. Just e to the power of 1 is the answer. But the process is to repeat what we had. The limit of ln y as x approaches infinity. We worked on it and we got it here. So what about y? Okay. Then you have to write e to the power of ln y or e to the power of 1. Simply put e. Now, most of the time, this is the method. I just quickly show you that you could do the second method, okay, as follows. Given this function y equals e to the power of x plus x to the power of 1 over x, we can write it in this format, and I hope you see that, okay? That comes from this property that e to the power of ln x is x. That's really the property that is being used here, okay, class? This is the property that is being used here. Okay. And so with that being the case, now you differentiate it. You're taking a limit, my apologies, as x approaches infinity, okay? And obviously, you can bring the 1 over x in front, okay? You can bring the 1 over x is in front. You can take this limit and work it out just the way we did with this one. And this is the one that you're taking a limit. So take the limit to the top, to the exponent, and work on this. Is this easier than this? Absolutely not. They're ultimately the same, class. They're absolutely the same. Ultimately, when you take these steps, you see they become the same. Do you have to go this route? No, that's your choice. Okay. All right. What about this one? Same situation. Let's look at this example where we get 0 to the power of 0. Okay. Because tan of 0 is 0. Okay. And so we will give it a name y. Okay. So y is this. So we take the natural log. That means x sits in front. Okay. So ln of the left equals ln of the right, and then x sits in front as a coefficient. If you will, the exponent is the power rule, okay? And so when you want to take the limit of ln y, again, whenever you're done, the answer is e to that power. To take the limit of this one, you look at it piece by piece, okay? And this becomes 0, and this becomes natural log of 0 from the right, which is negative infinity. And so it's one of those formats. You take one of them down. It's easier to take the x down, okay, class, and make it look like negative infinity over infinity, okay? And so we go through the process. This is a long one, class, but I just wanted to show you again the idea behind this various types of indeterminate forms. Okay. All right, so we are looking at a natural log. So we're going to flip this over. Tan 2x, we flip it over, it becomes 1 over tan 2x. Times the derivative of tan is secant squared. And then because it's 2x is 2. 1 over x, by now we know it's negative 1 over x squared. I'm assuming we have no problem with the bottom, class. We don't want to spend any time on that. You should know that. So let's recap. Natural log of tangent, flip over the tangent. The derivative of the tangent is secant squared. And because it's 2x, you need a 2. Okay? You need a 2. You rewrite this. This is a complex fraction, and the result is negative. You see, there's one negative sign, class, so we have one negative sign. We have 1 over tan 2x. We can take it down, make it tan 2x. We have secant, which is 1 over cosine. We can take it down. Negative 1 over x squared comes up in essence. With the 2 becomes negative 2x squared. I hope you see this is algebraic techniques, if you will. This is an algebraic techniques in conjunction with trigonometric. So one more time, 1 over tan 2x takes the tan 2x down. Secant is 1 over cosine. Okay, so we can write it as cosine in the denominator. Of course, it's squared, so it's squared. Okay. All right, now plug in, and you get 0 at top. You get 0 times cosine of 0 is 1. So it is 0 over 0. L'Hopital's rule again. Okay. So to use the L'Hopital's rule, perhaps if we change this tangent to sine over cosine makes life easier. Okay. If we make this sine over cosine, see, we can differentiate it faster. I've chosen this because it gives you a lot of information, not only L'Hopital's rule, it also reminds you of trigonometry. Tan is sine over cosine, everybody. So when we do that, one of those cosines go away, and we have only one of them now. So the top is sine times cosine. And I hope you remember it's the sine 2a. Remember the sine 2 alpha was 2 sine alpha cosine alpha, just reminding you of some trigonometric identity. So this becomes then therefore half of sine 4x, okay, class, sine 4x. And now we plug in, the top becomes 0, sine is 0, so 0 over 0 requires L'Hopital's rule again. The top gives you minus 4x. The bottom gives you 1/2 times. Sine gives you cosine. And then 4x gives you 4. That 1/2 and 4, they give us 2. In other words, if I want to write this class for you, would be 1/2 cosine and then 4. That's how we arrive at this. And now we replace the x with 0. The top becomes minus 4 times 0, okay, which is 0, and the bottom becomes 2 times 1. So it is important that it becomes 0 over 1 or 0. And as I mentioned, going back to the original question, the answer is the same, e to the power of the same thing. So your answer is e to the power of 0, which is 1. And again, I'm showing you the justification, but in short, just e to the power of whatever you got is the answer. All right. If we plug in 0, the base becomes 1 because this is 0, okay? And cotangent is infinity, so we have 1 to the power of infinity. And we're going to go through the same process. We're going to call this expression y. And I take the natural log of this, so cotangent becomes the coefficient. So ln of y is cotangent x, ln of 1 plus sine 4x. And now if I put cotangent in the denominator, it makes it a tangent. I hope you realize that, okay? That means when I say cotangent in the denominator, that means 1 over cotangent, or just simply put, just change this one to 1 over tangent. Okay, however you want to put that. Okay, and so now when you plug in, you get 0 over 0. It's obvious the sine is 0, tangent is 0, okay, when x is 0. So we are taking the limit of this piece, and therefore we can use L'Hopital's rule, okay, by taking the derivative of the top, which means flip it over, okay, 1 over 1 plus sine 4x, okay, then times the derivative of this expression is cosine 4x times 4 over tan x. The derivative of tan x is secant squared. So one more time, the top, flip this over, 1 over 1 plus sine 4x. And the derivative of this expression is cosine 4x times 4. And tan, the derivative is secant squared. Okay, everybody? Now, what happens when you plug in 0? This becomes a 4, this becomes 1, this becomes 1, and the answer is 4. So I hope you see that when you plug in cosine, okay, this becomes 4 times 1. This becomes 1 plus 0. And then over secant is 1 over cosine, and that's 1, and that's why we end up with 4. Therefore, your final answer is what? E to the power of 4. E to the power of 4, everybody. So you really don't have to do much, okay? It's important to see how you arrive at 4, and then, as I've mentioned, simply put your final answer would be e to that power. In this case, e to the